Hey guys, Jake here, coming at you with another math lesson. Today we're going to be continuing on and talking a bit more about finding zeros of a polynomial. Specifically, we're going to be talking about complex zeros and how they show up as conjugate pairs in polynomials. So I've made a few videos recently about finding zeros of polynomials, polynomial long division, synthetic division, all that kind of stuff. This kind of nicely wraps up a few of those concepts into one problem. So I wanted to talk a little bit more about complex zeros specifically, and then do an example that kind of showcases that. As well as another topic, which is finding the real zeros of a polynomial using, shoot, what was the name of that? The rational zero test, that's it. So we can use the rational zero test as well in this problem. So it's kind of a nice combo of a few different things. So first of all, let's talk a little bit about complex zeros in polynomials. And again, I kind of talked about this in my video, my last video, but I really want to be kind of taking a little bit more casual approach where I reveal a little bit more of my thought process behind different problems, behind reading math textbooks, because these are all really helpful skills that are important for you to know so that you can, excel in your pre-calc or college algebra class or any math class you're going to take, really. Trying to give you a fishing pole and teach you how to fish, not just give you the fish. Because truth is, reading a math textbook can feel like a foreign language because it basically is a foreign language. You need to learn how to read that foreign language and you can dominate any math topic. So let's get into this one right here. So let's start with kind of the textbook definition of this topic. Let f of x be a polynomial function with real coefficients. If a plus bi, where b does not equal 0, is a zero of the function, the conjugate a minus bi is also a zero of the function. So what does all this mean? Let's kind of break down the math, the words, explain how this actually makes sense in English. So first of all, f of x. We have some function named f. It is a function of x. X is the input variable, okay? We know it's a polynomial. I talked a bit in my video yesterday about what a polynomial is. Actually, more than a bit. I broke it down quite a bit. But a polynomial is basically a bunch of terms being added or subtracted together, where each term is a coefficient, constant number, times x raised up to some power. Okay, that's it. There is also a constant term with no x, potentially, but other than that, it's all just constants times x raised up to some positive whole number power. Okay. In this case, for this complex conjugate pair thing to work, we specifically need real coefficients in our polynomial. So what does a real coefficient mean? Take, for example, x squared plus 2x plus 1, okay? The coefficients, basically the constant numbers being multiplied by each term. So in this case, we could imagine a coefficient of 1. So 1, 2, 1. These are all real numbers, okay? So this does not apply if, for example, we have x squared plus 2x plus I. Now we have an imaginary coefficient. So that imaginary coefficient, this polynomial is not going to work with this rule. We need real coefficients, okay? Important thing to keep in mind there. Most polynomials you end up being asked to deal with are going to have real coefficients, but just in case you have one with imaginary numbers, just know this is not going to apply there. Okay, so if we know one of the zeros is a plus bi, where b is not 0, all that means, b is not 0, that means this coefficient of I is not 0. Because think about what would happen if it was. We would get a plus 0i. 0 times anything is 0. So this would just be a, which is just a real number, right? A plus bi is just a way to write complex numbers where you have a real part, which is represented by a, and an imaginary part. I is your imaginary term, where I is the square root of -1, right? So any imaginary number is going to have a real part and an imaginary part. If your imaginary part is 0, that just means you only have a real part, which is just a real number. So it's not a complex number at that point. So that's why b cannot be 0. So if we have a complex 0, so we have a real part and an imaginary part, we know that the conjugate of that complex number is also a zero of the function. So a conjugate in complex numbers is literally just flipping this sign from a positive to a negative. Basically, if you just take whatever your complex number was that you started with, make the imaginary part the negative of what it was before. So let's say let's just take this number down here, which we're about to get into. Let's say you have 5 plus 2i. You just make the imaginary part negative, and now you have a conjugate. So 5 minus 2i. If you start with a negative, you would go to a positive. So if you were given 5 minus 2i, you'd go to 5 plus 2i, and that would be a complex conjugate. So you just make whatever the imaginary part is negative of what it was. If it was negative, make it positive. If it was positive, make it negative. Keep the real part the same. So keep the 5 the same. Keep the a the same. And that's a conjugate. Okay? So basically, the reason why this is nice is if we're given some complex zero of a polynomial, we can immediately figure out another complex zero of the polynomial just by flipping the imaginary term to a negative. That's it. Okay. That's all this rule is really saying. So let's go ahead and apply it to an example here. Before I jump into that, though, I do really just want to point out my Precalculus study guide that I just came out with. If you want to go check it out, it should be a huge help to you, save you a ton of time on homework, studying, looking stuff up, all that kind of stuff. Nice little cheat sheet for you. Just go to jakesmathlessons.com/precalculus-study-guide. You can also scan that QR code up at the top right of your screen. So this type of a problem here, we're going to use the given zero to find all the zeros of the function. So right off the bat, we have this function, g of x equals x cubed minus 7x squared minus x plus 87. Okay. We know the problem told us this was given in the actual problem. One of the zeros is 5 plus 2i. Okay. So we can use this complex zeros occurring conjugate pairs rule that we just talked about to figure out right off the bat, we actually know another zero is 5 minus 2i. It's not quite given, but almost, as close as it gets. All we have to do is make that imaginary part negative, and we have another zero. It's pretty great. So now we need to think about what other zeros we might have. We're going to have some other zeros. We just got to figure out how to find them. Okay, because we have an x cubed polynomial, we know we should have, we could have zeros with higher multiplicity. But in this case, since 5 plus 2i is 1, 5 minus 2i is 1, we're not going to have complex zeros with higher multiplicity because they have to be conjugate pairs. So this is 2 of our zeros. We're going to need a third because it's an x cubed polynomial. It should have a third one. It's going to have to basically cross the x-axis at some point because whenever you have an odd degree polynomial, it's going to have to go, off in opposite directions to the left and to the right, right? It could go, that was really sloppy. Could go down to negative infinity as you go to the right and up to positive infinity as you go to the left, or vice versa. But if it's going off in both directions, infinitely up and infinitely down, it's eventually going to cross the x-axis somewhere. So it's got to have a real root. We know it's going to have a real root somewhere. The question is, where is it, right? We've already figured out 2 complex roots. We need a real root to kind of round out the puzzle here. So how can we find it? Well, that's probably where you want to use the rational zero test. That's probably going to be your best bet, okay? So the rational zero test, I just made a video about this recently. If you want to go check out the full explanation, I'll come back and put one of the info cards up there in the corner of your screen. Go check that out. So I'm not going to go into all the details here, but we definitely want to go into some of this. So basically, with the rational zero test, we can just take the coefficient of our leading term. Our leading term is x cubed. We have kind of an implied coefficient of 1. So we're going to take our coefficient of 1 and our constant term here of 87. And what we're going to do is we're going to put the factors of the coefficient, or not the coefficient, the constant term over the factors of the leading term coefficient. So factors of 87 over the factors of 1. Okay. This is a really nice leading coefficient because factors of 1 are just 1. So pretty easy. We really just need to figure out the factors of 87. So let's just think about how do you factor out the number 87? What numbers is it divisible by? Is it divisible by 1? Yeah, everything is divisible by 1. Okay. What else? Is it divisible by 2? Nope, it's an odd number. Is it divisible by 3? Yes, it is. 90 is divisible by 3. 87, shortcut, if you want to figure out if a number is divisible by 3, you can sum up the parts of it. So 8 plus 7 in this case is 15. 15 is divisible by 3. So that tells you that it's divisible by 3. Okay. What about 4? Nope, not even. Not going to be divisible by any even numbers. 5, no. 6, no. 7, no. Shouldn't be. Nope, not divisible by 7. 8, no. 9, no, because 90 is divisible by 9. If you minus 9 from that, you get down to 81. So not there. 10, nope, not divisible by 10. And at this point, we've gone past. So you really only needed to test up to the square root of the number. So the square root of 87 is between 9 and 10. Right? Because 9 squared is 81, 10 squared is 100. So it's somewhere between 9 and 10. So if we think about factors, we really only need to go up to 10. Once we get up to 10, we've double checked all the factors. Now we just need to figure out what factors match up with these two. So what is 87 divided by 3? Well, 90 divided by 3 is 30. So 87 divided by 3 should be 29. Because it's just 90 minus 3. So one less 3 in there. And then 87 divided by 1 would be 87. Okay? So there's all the factors of 87. There's only 4 of them. Watch that rational zero test video I made. There was way more factors. Then what? So this is a kind of a nice, convenient, small list. Then what we need to do is make all these positive and negative. We want the positive and negative of each of these. So basically there's 8 possible real rational roots to this polynomial. Because if we put it all over plus or minus 1, that's not really going to do anything, right? Because any number divided by 1 is just 1. Obviously, we want the plus and minus, but we want the plus and minus of all these too, so that's not really going to add anything else. So really, we have basically negative 1, 1, negative 3, 3, negative 29, positive 29, negative 87, and positive 87. These are our 8 possible real roots to this polynomial. A couple ways we could go about this, testing this out. We could just basically take each one of these and plug them into the function and see if we get 0. That's probably the easiest option. The other option you could do is do synthetic division on this polynomial and see which one of these zeros will actually give you a remainder of 0. If you go through synthetic division and get a remainder of 0, that tells you that factor is a factor and that 0 is a 0. I think it's easier to just plug numbers in, so I'm just going to do that. So let's just kind of think about these one by one. So negative 1 we'll start with. So g of negative 1. And I'm going to kind of speed, I'll show you the first one a little bit more detail, but then I'll speed up a little bit. So negative 1 cubed minus 7 times negative 1 x, or negative 1 squared, sorry, minus negative 1 in parentheses plus 87. Okay? Negative 1 cubed is negative 1. Negative 1 squared is positive 1 times negative 7 is negative 7. Minus negative 1 is plus 1 plus 87. Yeah, clearly, so those are going to cancel. Minus 7. This is clearly not 0. It's 80. Okay, so that does not work. So it's not negative 1. We can cross that off the list. Okay, what about g of 1? And again, I'm going to speed up through this a little bit. 1 cubed is 1. 1 squared is 1 times negative 7 is minus 7. Minus 1 plus 87. Again, clearly not 0. I'm not even going to bother adding that up. It's not even close. Okay, so it's not 1. What about negative 3? Negative 3 cubed minus 7, negative 3 squared minus negative 3 plus 87. Okay, adding this all up. Negative 3 cubed is minus 27. Negative 3 squared is 9 times negative 7 is negative 63 plus 3 plus 87. So negative 27 plus 87 is plus 60. Minus 63 is negative 3. Plus 3 is 0. So this actually gives us 0. So that tells us negative 3 is actually a 0 of this function. Okay? Like I said, since this is a cubic function, we know that it's going to have at most 3 zeros. We already found 2 up here, right? And we just found a third. So, pretty easily we can just say that none of those are going to work because we've already found all the zeros that this function possibly could have. We're not going to end up finding more zeros than, what the degree of the polynomial is. And, if you wanted to, you could, let me just show one other thing on the screen here, just to kind of confirm. Come on. You could graph this function. So if we graph this function, we can see, or plug it into Wolfram Alpha, it'll tell us just to confirm our work, check our work here. You can see, like I said, we have kind of off to the left, it's pointing, down to negative infinity off to the left, pointing up to positive infinity off to the right. So we know that it's going to have to cross the x-axis and give us a real root somewhere. And if you come down here, you can see it has a real root at x equals negative 3, just like we got. And then complex roots at 5 plus 2i and 5 minus 2i. So it perfectly confirms exactly what we found for all 3 of our zeros. So that's perfect. All right. So that really is kind of the process there. Like I said, I have made a few other videos on similar topics that go along well with this. The rational root test, the polynomial long division, synthetic division. So go check out some of those videos. I'll put the rational root test video right over there. You can go check that out. That should be really helpful for you. If you found this video helpful, do me a favor, hit that like button, and go check out that pre-calc study guide. See you next time.